Question 5D from the 2009 paper. We've got a particular line spectrum examined using a diffraction grating, 300 lines per millimetre with the light coming in along the normal, so as you would expect it to be, straight along. And it's found that a line at 24.46 degrees contains both red and blue-violet and components within it. And we need to find out if there are any other angles at which both red and blue-violet components are observed. So this could be a bit of a tricky question. The first thing to do is give a quick sketch of what we know, and then maybe perform some calculations to find out what else we can work out. So diffraction grating, lots of gaps. This is a representation, obviously not to scale. There's our incoming ray, and we've got our screen, and the center is here. This is the center axis, 0 position for X, and we're told we've got one diffraction grating, one bright fringe with the which contains both red. I'm going to draw these together. So red and a blue-violet on the same section. Okay. So, and we're told what angle that is, so I'll draw in the angle for that, which is, let's see, about, I have to draw that slowly, so the angle theta from the center, so there's the center line, is 24.46 degrees. So from this we don't know what values of n this is. We'll have an n value for the red, and we're going to have an n value for the blue purple. And so we pretty much need to find out what those are. That's going to help us, because then we know what, well, you'll see, it's a little bit awkward to explain, but it's to do with the ratio of the n values for the red and n values for the purple. So what we can do is find out from n lambda equals d sine theta. We know theta, we know d, which is 300 lines per millimetre, and we can calculate this portion here, the n lambda part, and then we just divide by, because the n lambda part's going to be the same, has to be the same for the same angle that's here. So we just have to divide by those wavelengths to find out what our two n values are. So if we do that, d sine theta, using this data, it gives us 1380 nanometers, and this in turn, when we divide it by those ranges, I mean there's only one value of n for each that will fit in with those ranges, we find that the n for red is 2, so n for red equals 2, and we find, because it's about 1380 divided by, say, 640 to 750, somewhere in that range, you can only get 2. You can't get 3 and you can't get 1. 2 fits. And then the n value for the purple or the violet or the blue or whatever you want to call it works out to be 3. Okay, so 3 times 360 and 3 times 490, that falls within that range of 1380 falls within that range anyway. And if you go up to 4, then it's too much, much too much, and if you go down to 2, it's much too little. So those two values are our n values. And so let's just draw that out in a little bit more detail. So this means this is the second red one. So as far as that distance of x, we've got 2 within that same distance x. So we've got 2 fringes. You've also got the centre fringe, but we're not too worried about that with the counting. So we've got 2 fringes. And going back to the purple, the blue purple, we've got 3. So this distance x is actually divided up into, this is the third fringe, so we've got the centre one, and then we've got 2 in between here. 1, 2, 3, evenly spaced. Okay, I don't know how well I've done this evenly spaced. So yeah, so x is the same for both of them, but you've got the third one for the blue purple, and the second one for the red. So what we need to do is keep drawing, if we were to draw this, keep drawing them at the same spacing that we have, where are we? Same spacing that we have, and see when they next overlap. So we've got another 1, 2, 3, and we're going to find that 6, 1, 2, 3, 4, 5, 6, n equals, in purple equals 6, and red, n for the red right, equals 4. Is going to be another one that works, which is that same ratio of 2 to 3. If you divide 6 by 2 you get 3, so 4 by 2 you get 4, and that's the same ratio that we had down here with this. Okay, so what do we do then? We need to calculate the next one up, so 6 to 4 is our ratio. If we do calculation for n lambda, where everything is exactly the same, except n now goes to 6, and lambda is still the same wavelength, and there d is still the same, and we're trying to find theta. And it turns out when you do that, with 6 and with 4, for the two different wavelengths, the blue and the violet and the red, you end up with theta equaling 55.9 degrees. Okay, so 55.9 degrees. That's within the 90 degree range. So that's the other angle which we're actually looking for, at which both blue and red occur in the same location. Now, if we go up to the next ratio of 3 to 2, which will be, let's see, 12 to, is that right? Yeah, so it's 3 to 2. So, no, 9 to 3. Does that work? 9 to 3. That doesn't fit in the same ratio, does it? Sorry, getting myself mixed up. 9 to 6 would be the next, with 9 being red and sorry, 6 being red and purple there. But if you keep going up with that ratio of 3 to 2, you'll find that this provides an angle greater, so theta would be greater than 9 degrees, so it doesn't work. So the only angle other than that is 55.9 degrees, and then you're there. Nice and easy. Replay it if you're not sure how to work that out. I think the diagram helps very much.